Tonight, we are going to embark on a journey to the very edge of what physics can tell us about reality. We are going to explore one of the most profound and controversial ideas in modern theoretical physics, a concept that has sparked fierce debate among the greatest minds of our generation and continues to challenge everything we thought we understood about the universe. We are going to discover the Firewall Hypothesis, a radical proposal that suggests the boundary of a black hole might not be the peaceful, unremarkable threshold that Einstein's theory predicted, but instead a blazing wall of destruction that would incinerate anything foolish enough to cross it. This is not merely an academic puzzle. The firewall paradox strikes at the very heart of our most fundamental theories of nature. It exposes a deep conflict between quantum mechanics and general relativity, the two pillars upon which all of modern physics rests. And the resolution to this paradox, whatever it turns out to be, will likely revolutionize our understanding of space, time, gravity, and the very fabric of existence itself. Before we begin our exploration, if you find yourself drawn into these deep contemplations of the cosmos, consider subscribing to the channel. These journeys through the mysteries of the universe are crafted to help you drift into peaceful contemplation, whether you're seeking rest or simply a moment of profound wonder at the nature of reality. Now let us begin our descent toward the most mysterious objects in the cosmos. Picture yourself floating in the vast emptiness of space, far from any star or planet, surrounded only by the cold silence of the void. In the distance, you observe something strange. There is a region of space where the stars behind it seem to bend and distort, their light curving around an invisible boundary, like water flowing around a stone in a stream. This is a black hole, an object so dense that its gravity warps the very geometry of spacetime, creating a region from which nothing, not even light itself, can escape. Black holes have captured the human imagination ever since their existence was first predicted by the equations of Einstein's general theory of relativity. They represent the ultimate triumph of gravity, the final fate of massive stars that have exhausted their nuclear fuel and can no longer resist the inward pull of their own weight. When such a star collapses, it compresses matter into an ever smaller volume until it reaches a point of theoretically infinite density, a singularity hidden behind an invisible boundary called the event horizon. The event horizon is perhaps the most distinctive feature of a black hole. It is not a physical surface, not a wall or membrane that you could touch. Instead, it is a mathematical boundary, a point of no return beyond which the escape velocity exceeds the speed of light. Anything that crosses this threshold, whether matter, light, or information, is destined to fall inward toward the singularity, never to return to the outside universe. For decades, physicists believed they understood what would happen if you were to fall into a black hole. According to Einstein's equivalence principle, one of the foundational ideas of general relativity, there is no way to distinguish between floating freely in empty space and falling freely under the influence of gravity. This means that as you approach and cross the event horizon of a sufficiently large black hole, you should notice nothing unusual. The curvature of space-time at the horizon of a massive black hole is actually quite gentle, far gentler than what you experience standing on the surface of the Earth. You would simply drift across this invisible boundary, unaware that you had passed the point of no return, continuing your fall toward the singularity where eventually the tidal forces would tear you apart. This benign picture of crossing the event horizon became known informally as the no drama scenario. It suggested that the event horizon, despite its profound significance as the boundary between our universe and whatever lies within the black hole, was physically unremarkable. A freely falling observer would experience nothing special there. No jolt, no flash of light, no indication whatsoever that they had crossed the most significant boundary in all of physics. But in 2012, 4 physicists published a paper that shattered this comfortable picture. Ahmed Al-Mehri, Donald Marolf, Joseph Polchinski, and James Sully, working at the University of California, Santa Barbara, demonstrated that the peaceful passage across the event horizon was fundamentally incompatible with the basic principles of quantum mechanics. Their argument, which became known as the AMPS firewall paradox after the initials of its authors, suggested that instead of drifting peacefully through the horizon, an infalling observer would be instantly incinerated by a blazing wall of high-energy particles, a firewall that would destroy anything attempting to enter the black hole. This was a shocking conclusion, and it sent ripples through the theoretical physics community. The Firewall Hypothesis challenged Einstein's equivalence principle, one of the most thoroughly tested and trusted principles in all of physics. It suggested that quantum effects could create violent, dramatic phenomena at the event horizon, in a region where gravity is relatively weak and classical physics should reign supreme. And it exposed a deep tension between our 2 most successful theories of nature, a tension that had been lurking beneath the surface for decades, but had now erupted into the open. To understand the firewall paradox, we must first understand the problem it was trying to solve. We must journey back to the 1970s, to a revolutionary discovery made by a young physicist named Stephen Hawking, a discovery that would eventually lead us to the edge of this blazing boundary. The story of the firewall begins with one of the most remarkable theoretical predictions in the history of physics. In 1974, Stephen Hawking was working on combining quantum mechanics with general relativity, attempting to understand how quantum effects might manifest in the extreme gravitational environment near a black hole. What he discovered was utterly unexpected and would change our understanding of black holes forever. Hawking realized that black holes are not truly black. They emit radiation, now called Hawking radiation in his honor, and this radiation causes them to slowly lose mass and eventually evaporate entirely. This discovery overturned the prevailing view that black holes were eternal objects, prisons, from which nothing could ever escape. Instead, Hawking showed that quantum mechanics allows particles to tunnel out of the black hole's gravitational grip, carrying away energy and causing the black hole to shrink over astronomical timescales. One way to understand the mechanism behind Hawking radiation is through the strange quantum nature of the vacuum. In quantum field theory, empty space is not truly empty. It seethes with virtual particle pairs, constantly popping into existence and then annihilating each other. Their brief existence allowed by the uncertainty principle that governs the quantum realm. These virtual particles normally cancel each other out before they can be observed, leaving no trace of their fleeting existence. Near the event horizon of a black hole, something remarkable can happen. If a pair of virtual particles forms very close to the horizon, one particle may fall into the black hole while its partner escapes to infinity. In this picture, the escaping particle becomes real, carrying positive energy away from the black hole, while the infalling particle effectively carries negative energy into the black hole, reducing its mass. From the perspective of a distant observer, the black hole appears to be radiating particles, glowing with a faint thermal glow, whose temperature is inversely proportional to the black hole's mass. While this virtual particle picture is a useful conceptual model, the full derivation of Hawking radiation requires more sophisticated quantum field theory calculations in curved spacetime. For a typical stellar mass black hole, this radiation is incredibly faint, far too weak to detect with any current or foreseeable technology. The temperature of such a black hole is a tiny fraction of a degree above absolute zero, colder than the cosmic microwave background radiation that fills the universe. Only for extremely small black holes, far smaller than any that could form from stellar collapse, would the Hawking radiation be significant enough to observe directly. But the theoretical implications of Hawking radiation were profound and deeply troubling. The problem was not the radiation itself, but what it seemed to imply about the fate of information that falls into a black hole. In quantum mechanics, information is conserved. The complete quantum state of a system at any moment in time contains all the information needed to reconstruct the state at any other moment, whether in the past or the future. This property, called unitarity, is fundamental to the mathematical structure of quantum mechanics. Without it, the probabilities of different outcomes would not add up to one, and the entire predictive framework of quantum theory would collapse. Hawking's calculation, however, suggested that black holes violate unitarity. The radiation they emit appears to be purely thermal, carrying no information about what fell into the black hole in the first place. A black hole formed from the collapse of a massive star would emit exactly the same Hawking radiation as one formed from an equivalent mass of hydrogen gas or antimatter or anything else. All the rich quantum information that characterized the infalling matter seemed to be erased, replaced by a featureless thermal glow. This presented a stark dilemma. If the black hole eventually evaporates completely, disappearing into a final burst of Hawking radiation, where does the information go? It cannot remain in the black hole, because the black hole no longer exists. It does not appear to be encoded in the Hawking radiation, which is purely thermal. The information seems to simply vanish from the universe, violating one of the most fundamental principles of quantum mechanics. This puzzle became known as the black hole information paradox, and it has occupied some of the greatest minds in theoretical physics for nearly half a century. Hawking himself initially believed that information truly was lost in black holes, that quantum mechanics would have to be modified to accommodate this new feature of nature. But many physicists found this conclusion deeply unsatisfying. The conservation of information is not merely a convenient assumption. It is woven into the very fabric of quantum mechanics. Abandoning it would require reconstructing physics from the ground up. In 1993, the Canadian physicist Don Page, who had been Hawking's doctoral student, made a crucial observation that would eventually lead to the firewall paradox. Page considered the entanglement between the Hawking radiation and the black hole that emits it. When a pair of virtual particles forms near the horizon and one escapes as Hawking radiation while the other falls in, these two particles are quantumly entangled. Their quantum states are correlated in a way that has no classical analog, so that measuring one particle provides information about the other. Page realized that if black hole evaporation is truly unitary, preserving information as quantum mechanics demands, then the entanglement entropy of the Hawking radiation cannot increase forever. Initially, as the black hole emits radiation, the entropy of the radiation should increase, reflecting the growing number of emitted particles and their entanglement with the remaining black hole. But after the black hole has lost roughly half of its original entropy, something must change. The radiation must begin to become entangled with earlier radiation that was already emitted, and the entanglement entropy must begin to decrease, eventually returning to zero when the black hole has completely evaporated. The time at which this transition occurs became known as the page time, and it marks a critical moment in the life of an evaporating black hole. Before the page time, the Hawking radiation is primarily entangled with the black hole interior, exactly as Hawking's original calculations suggested. But after the page time, the new radiation must be primarily entangled with the old radiation, allowing information to gradually leak out as the black hole continues to shrink. The behavior of entanglement entropy that Page described, increasing initially and then decreasing after the page time, is now called the Page curve. For decades, physicists believed that the true quantum description of black hole evaporation must reproduce this curve, but no one could show how. Hawking's semi-classical calculation stubbornly predicted monotonically increasing entropy, contradicting the requirements of unitarity. This mismatch lay at the heart of the information paradox and would eventually lead physicists to the radical proposal of firewalls. The tension between quantum mechanics and the peaceful picture of black hole horizons did not go unnoticed in the years following Hawking's discovery. In the early 1990s, several physicists, most notably Leonard Susskind, Gerard 't Hooft, and John Preskill, began developing a framework that they hoped would resolve the paradox without abandoning either quantum mechanics or general relativity. This framework became known as black hole complementarity. The central insight of black hole complementarity was that the apparent contradiction between different descriptions of black hole physics might not be a true contradiction at all. Instead, it might reflect a subtle feature of quantum gravity, a limitation on what any single observer can measure and experience. Consider two observers: Alice, who bravely decides to fall into a black hole, and Bob, who remains safely outside. According to general relativity, Alice should experience nothing unusual as she crosses the event horizon. She drifts through the invisible boundary, continuing her fall toward the singularity, where she will eventually be destroyed by the enormous tidal forces. From her perspective, the information she carries falls into the black hole along with her, eventually meeting its fate at the singularity. But from Bob's perspective, things look very different. He never sees Alice cross the horizon. Due to the extreme time dilation near the event horizon, Bob sees Alice's fall slow down asymptotically, her image becoming increasingly red-shifted and frozen at the horizon. To Bob, it appears that Alice is smeared across a thin membrane, called the stretched horizon, a surface located about 1 Planck length outside the mathematical event horizon. The information Alice carried appears to be absorbed by this membrane, heated to enormously high temperatures, and eventually re-emitted as Hawking radiation, which Bob can, in principle, collect and decode. So what actually happens to the information? Does it fall through the horizon with Alice? Or does it remain on the stretched horizon and eventually escape in the Hawking radiation? Black hole complementarity proposed a radical answer. Both descriptions are correct, and they are complementary in the quantum mechanical sense, like the wave and particle descriptions of light. No single observer can see both descriptions simultaneously, because doing so would require being both inside and outside the black hole, which is impossible. The principle of complementarity asserts that as long as no single observer can witness a contradiction, there is no actual contradiction. This resolution depended crucially on the idea that information could exist in two places at once, at least from different observers' perspectives, without violating the no-cloning theorem of quantum mechanics, which forbids the creation of exact copies of quantum states. The key was that Alice and Bob could never compare notes. Once Alice crosses the horizon, she is forever cut off from the outside universe. She cannot send a message to Bob telling him what she observed inside, because no signal can escape from within the event horizon. The two descriptions, interior and exterior, are causally disconnected, and the apparent duplication of information is unobservable. For nearly 2 decades, black hole complementarity was widely accepted as a satisfying resolution to the information paradox. It preserved the unitarity of quantum mechanics by ensuring that information eventually escaped in the Hawking radiation, while also preserving the equivalence principle by maintaining that Alice experienced nothing unusual at the horizon. The two requirements seemed incompatible, but complementarity showed they could coexist in the strange quantum world. But there was a subtle tension lurking within this framework, a tension that would eventually explode into the firewall paradox. The resolution of black hole complementarity depended on the assumption that certain quantum experiments could never be performed, certain comparisons could never be made. And in 2012, Almheri, Marolf, Polchinski, and Sully showed that this assumption was wrong. The AMPS paper, published in July 2012, sent shockwaves through the theoretical physics community. It presented a deceptively simple argument that demonstrated a fundamental inconsistency in black hole complementarity, forcing physicists to abandon one of 3 seemingly unassailable principles. The argument hinged on a quantum mechanical property called the monogamy of entanglement, and it revealed that the peaceful passage through the event horizon was incompatible with the preservation of information. To understand the AMPS argument, we must first understand monogamy of entanglement. In quantum mechanics, entanglement is a special kind of correlation that has no classical analog. When 2 particles are entangled, measuring one provides information about the other, even if they are separated by vast distances. This correlation is not due to any hidden variables or predetermined outcomes. It is a fundamental feature of quantum reality. But there is a crucial limitation on entanglement. A quantum system cannot be maximally entangled with 2 different systems simultaneously. If particle A is maximally entangled with particle B, then A cannot be entangled with particle C at all. This property is called monogamy of entanglement, and it is a mathematical consequence of the structure of quantum mechanics, as fundamental as the uncertainty principle. Now consider what happens when a black hole emits Hawking radiation. According to Hawking's original calculation, each particle of outgoing radiation is entangled with a partner particle that falls into the black hole. This entanglement between the outgoing particle and its infalling partner is what allows Alice to experience a smooth passage through the horizon. The entanglement ensures that the quantum state near the horizon is the vacuum state, with no high-energy particles or dramatic effects. But here is the problem. After the page time, when the black hole has emitted more than half its entropy, the outgoing Hawking radiation must also be entangled with the radiation that was emitted earlier. This is what the page curve requires. The late-time radiation must be correlated with the early-time radiation in a way that allows information to be recovered. The entanglement entropy of the radiation must begin to decrease, and this can only happen if the new radiation is entangled with the old. So the outgoing Hawking particle must be maximally entangled with two different systems: its infalling partner just behind the horizon, and the previously emitted Hawking radiation far away. But monogamy of entanglement forbids exactly this. A particle cannot be maximally entangled with two independent systems simultaneously. Something has to give. AMPS argued that there were only three ways to resolve this contradiction, and all three required abandoning a cherished principle of physics. The first option was to give up unitarity, accepting that information truly is lost in black holes, and quantum mechanics must be modified. This was Hawking's original position, but most physicists found it deeply unappealing. Abandoning unitarity would undermine the entire predictive framework of quantum mechanics and would likely require a radical reconstruction of physics. The second option was to give up the idea that effective field theory, the standard framework for describing quantum fields in curved spacetime, is valid near the horizon. This would mean that quantum gravity effects somehow become important even when the spacetime curvature is negligible, a possibility that contradicted everything physicists thought they knew about when quantum gravity should matter. The third option was to give up the equivalence principle, accepting that something dramatic does happen at the horizon of an old black hole. If the outgoing Hawking particle is not entangled with an infalling partner, then the quantum state near the horizon is not the vacuum. Instead, it is an excited state filled with high-energy particles. An observer falling through the horizon would encounter this wall of energetic particles and be instantly destroyed. This was the firewall. AMPS argued that the firewall was actually the most conservative of the three options. It preserved unitarity and the validity of effective field theory in regions where we expect them to hold, at the cost of modifying physics only at the special surface of the event horizon. The equivalence principle would be violated, but only in this one specific context, in a region that no external observer could ever probe directly. The response to the AMPS paper was immediate and intense. Physicists around the world grappled with the implications, searching for flaws in the argument or alternative resolutions that might preserve all three principles. Workshops were organized, papers were written by the dozens, and some of the most prominent figures in theoretical physics weighed in on the debate. The Stanford Institute for Theoretical Physics organized an informal workshop in late 2012 that brought together many of the leading researchers working on the problem. For 2 days, participants brainstormed possible resolutions, filling blackboards with equations and debating the merits of various approaches. The atmosphere was charged with excitement and frustration in equal measure, as participants recognized both the significance of the problem and its difficulty. Raphael Bousso, of the University of California, Berkeley, called the firewall concept outrageous, complaining that a firewall simply cannot appear in empty space any more than a brick wall can suddenly appear in an empty field and smack you in the face. His objection captured the visceral reaction many physicists felt to the idea that the smooth geometry of general relativity could be so dramatically violated. Joseph Polchinski, one of the authors of the original paper, acknowledged that the idea seemed crazy, but argued it was the least crazy of the available options. He emphasized that the AMPS argument was not proposing firewalls as a desirable outcome, but rather deriving them from principles that most physicists accept. If the conclusion seemed absurd, the remedy was to find a flaw in the argument, not to reject the conclusion out of hand. Leonard Susskind, one of the architects of black hole complementarity, initially defended his earlier framework, but eventually came to accept that the AMPS argument revealed genuine issues that needed to be addressed. His response evolved over time, moving from defense of complementarity to exploration of new ideas like ER equals EPR that might resolve the paradox in a deeper way. The firewall debate also attracted attention from physicists outside the immediate circle of quantum gravity researchers. Quantum information theorists, who had developed many of the concepts and tools used in the AMPS argument, became active participants in the discussion. Their expertise in entanglement, quantum channels, and information theoretic constraints proved invaluable in clarifying the structure of the paradox and evaluating proposed resolutions. John Preskill of the California Institute of Technology, a leading figure in quantum information theory, described the firewall as odious while acknowledging the strength of the AMPS argument. He emphasized that the paradox forced physicists to take seriously the idea that quantum information constraints could have dramatic physical consequences, a perspective that quantum information theorists had long advocated. The debate extended beyond technical arguments to questions about the nature of scientific reasoning and the role of thought experiments in physics. Critics of the firewall pointed out that no one could ever actually perform the experiment AMPS described, collecting Hawking radiation over cosmological timescales and then diving into an old black hole. If the experiment was physically impossible, did the paradox really have physical content? Proponents responded that the thought experiment was a legitimate tool for exposing inconsistencies in our theories, regardless of whether it could be performed in practice. Einstein had used thought experiments extensively in developing relativity, imagining observers falling in elevators or racing alongside light beams. The fact that these experiments could not literally be performed did not diminish their role in revealing the structure of physical law. The firewall debate also highlighted the peculiar status of black hole physics within modern science. Black holes are among the most exotic objects predicted by general relativity, yet they are now routinely observed through gravitational waves and direct imaging. The physics near their horizons, however, remains purely theoretical, inaccessible to any conceivable measurement. This creates a situation where the most profound questions can only be addressed through theoretical reasoning, with no possibility of experimental test. Some physicists view this situation with concern, worrying that theoretical physics may be drifting away from its empirical roots. Others see it as an opportunity, a chance for pure thought to guide us toward deeper understanding in domains where experiment cannot reach. The firewall debate embodies this tension, challenging physicists to develop criteria for evaluating theories that cannot be directly tested. The firewall debate exposed just how poorly understood black hole physics really is. For all the progress that had been made since Hawking's original discovery, fundamental questions remained unanswered. What is the interior of a black hole really like? Where does the information go? How do quantum mechanics and general relativity combine to describe these extreme objects? The firewall paradox did not answer these questions, but it sharpened them dramatically, revealing that our current understanding is fundamentally incomplete. The paradox also raised deeper questions about the relationship between theoretical physics and observable reality. Black holes lie at the intersection of our most profound theories, yet their interiors are forever hidden from direct observation. The best we can do is develop theoretical frameworks that are internally consistent and compatible with the observations we can make, such as the properties of gravitational waves from merging black holes or the shadow images captured by the Event Horizon Telescope. If the firewall hypothesis is correct, what would this blazing boundary actually be like? What would an observer experience as they approached and attempted to cross the event horizon of an old black hole? The answer is both dramatic and deeply strange, representing a complete departure from the gentle passage that Einstein's theory seemed to promise. Imagine yourself falling toward a black hole that has been evaporating for longer than its page time. According to the firewall hypothesis, you would initially notice nothing unusual. Space and time would appear normal, with no visible indication of the boundary you were approaching. The event horizon is not a physical surface that you can see. It is defined only by the inability of light to escape, and from your infalling perspective, light would still appear to move normally in all directions. But as you reach the horizon, according to the firewall hypothesis, you would encounter something terrifying. Instead of drifting peacefully through an invisible boundary, you would suddenly find yourself immersed in a seething maelstrom of high-energy particles and radiation. Based on theoretical calculations, the temperature at the firewall could be enormous, possibly comparable to the Planck temperature, the highest temperature allowed by physics, around 10 to the 32 degrees. This is a temperature so extreme that our current theories cannot reliably describe what would happen. But if the firewall hypothesis is correct, survival would almost certainly be impossible. The firewall would incinerate anything attempting to cross the horizon, converting matter into high-energy radiation in an instant. There would be no gentle passage to the singularity, no opportunity to observe the bizarre geometry of the black hole interior. The firewall would mark the true boundary of the black hole, a barrier as impenetrable as any physical wall, even though it is made only of quantum excitations in the fabric of spacetime itself. This is a shocking violation of the equivalence principle, which tells us that free fall should be indistinguishable from floating in empty space. According to Einstein, an observer in free fall should be unable to determine their gravitational environment through any local measurement, but encountering a firewall would certainly count as a dramatic local effect, a clear indication that you are not simply floating in empty space, but were instead at a very special location in the universe. The violation of the equivalence principle is what makes the firewall hypothesis so disturbing to many physicists. The equivalence principle has been tested to extraordinary precision in laboratory experiments, and it is the foundation upon which general relativity is built. To abandon it, even at the special location of a black hole event horizon, feels like a betrayal of one of the most beautiful and successful theories in the history of science. But the AMPS argument seems to leave no other option, at least within the framework of conventional physics. If information is preserved and effective field theory is valid, then something must destroy the entanglement between the outgoing Hawking particle and its infalling partner. A firewall is the most straightforward way to accomplish this, even if it requires accepting consequences that seem almost impossible to believe. There is an important subtlety to the firewall hypothesis that is often overlooked. The firewall would only form after the page time, when the black hole has emitted more than half of its original entropy. For a stellar mass black hole formed from the collapse of a star a few times more massive than the Sun, the page time would be unimaginably long, many orders of magnitude longer than the current age of the universe. Such black holes would not yet have firewalls. They would still offer peaceful passage to any brave or foolish observer. Only very small black holes, or black holes that have been evaporating for cosmological timescales far exceeding the present age of the universe, would have reached the stage where firewalls become necessary. This means that the firewall hypothesis, while theoretically profound, has no practical consequences for any black holes we might actually observe or interact with. It is a statement about the fundamental nature of quantum gravity, not a prediction about astrophysical phenomena we could hope to measure. Nevertheless, the conceptual implications are enormous. If firewalls exist, then the interior of an old black hole is fundamentally different from what general relativity predicts. There may be no interior at all in the conventional sense. The event horizon may not be an invisible boundary that observers pass through smoothly, but a genuine end to spacetime, a wall beyond which nothing exists. Some physicists have compared the firewall to a new kind of singularity, not hidden at the center of the black hole, but exposed at its very edge. This analogy suggests that just as the singularity at the center represents a breakdown of general relativity, where the curvature becomes infinite and our equations fail, the firewall might represent a breakdown at the horizon, where quantum effects overwhelm the classical description and something entirely new must take over. Whether this interpretation proves correct remains to be determined. This is both troubling and exciting. It suggests that black holes are even stranger than we thought, harboring physics at their boundaries that our current theories cannot fully describe. And it points the way toward a deeper understanding, a true theory of quantum gravity that can resolve the paradoxes and reveal the nature of these cosmic enigmas. The firewall paradox did not go unanswered. In the years following the AMPS paper, physicists proposed a variety of alternative resolutions, each representing a different way of thinking about the relationship between quantum mechanics, gravity, and information. Among the most influential of these proposals was the ER equals EPR conjecture, put forward by Juan Maldacena of the Institute for Advanced Study and Leonard Susskind of Stanford University in 2013. The name of this conjecture is a compact equation that links two of Einstein's most famous contributions to physics. ER refers to Einstein-Rosen bridges, better known as wormholes, theoretical tunnels through space-time that connect distant regions of the universe. EPR refers to the Einstein-Podolsky-Rosen paradox, the thought experiment that first highlighted the strange, non-local correlations of quantum entanglement. The conjecture proposes that these two phenomena, seemingly unrelated, are actually two aspects of the same underlying reality. The idea arose from considering what happens when two black holes are quantum mechanically entangled. In the context of the ADS-CFT correspondence, a powerful theoretical tool that relates gravitational physics in a higher dimensional space to quantum field theory on its boundary, Maldacena and Susskind showed that entangled black holes are connected by a wormhole. The wormhole is non-traversable, meaning that no information or observer can pass through it to travel from one black hole to the other. But it exists as a geometric connection, a shortcut through the interior of spacetime. The ER equals EPR conjecture generalizes this observation, proposing that any entangled quantum systems are connected by some form of wormhole. Based on this framework, when two particles are entangled, there could be a microscopic wormhole linking them, a thread of space-time geometry that reflects their quantum correlation. Such a wormhole would be far too small to have any observable consequences, but if it exists at a fundamental level, it would connect the particles in a way that transcends the ordinary notion of spatial separation. How does this help with the firewall paradox? Recall that the paradox arises because the outgoing Hawking particle must be entangled with both its infalling partner and the previously emitted radiation, violating the monogamy of entanglement. But if ER equals EPR is correct, then the Hawking particle and the early radiation are connected by wormholes. And here is the key insight. If those wormholes are part of the same network as the wormhole connecting the Hawking particle to its infalling partner, then the two entanglements might not be independent after all. In other words, the firewall paradox might arise from incorrectly treating the infalling partner and the early radiation as separate systems. If they are actually connected through the wormhole network, then the monogamy of entanglement is not violated, and there is no need for a firewall. The infalling observer can pass peacefully through the horizon because the quantum correlations that seem to require a firewall are actually distributed through the wormhole structure in a way that preserves both unitarity and the equivalence principle. This is a beautiful and audacious idea, but it remains controversial and incompletely developed. The conjecture requires that wormholes exist even for ordinary particles, a radical extension of general relativity that has not been confirmed, and it is unclear how the wormhole picture can be made consistent with all the constraints of quantum mechanics, including the monogamy of entanglement that motivated the firewall in the first place. Nevertheless, ER equals EPR has been enormously influential, inspiring a wave of research into the connection between quantum entanglement and the geometry of spacetime. Based on what we know from these investigations, entanglement could be the glue that holds spacetime together, with the smooth fabric of the universe emerging from the vast web of quantum correlations between its fundamental constituents. This perspective, sometimes called it from qubit, represents a profound shift in how physicists think about the nature of reality. Mark van Ramsdonk of the University of British Columbia has been a leading proponent of this view, conducting thought experiments that suggest removing entanglement between regions of a quantum system is equivalent to tearing apart the space-time that connects them. If you take away the entanglement, your space-time just falls apart, he has explained, adding that space-time really is just a geometrical representation of the entanglement structure of these underlying quantum systems. These statements would have seemed outrageous just a decade ago, but now represent a mainstream perspective in theoretical physics. If this view is correct, then the firewall paradox may be pointing us towards something even deeper than the physics of black holes. It could be revealing the quantum origins of spacetime itself, suggesting that geometry and gravity are not fundamental, but emerge from the more primitive structure of quantum entanglement. The firewall would then be not a real phenomenon, but a signal that our classical description of spacetime is breaking down, an indication that we need to think in terms of the underlying quantum degrees of freedom rather than the emergent classical geometry. This interpretation remains speculative, but has gained significant support within the theoretical physics community. Another proposed resolution to the firewall paradox comes from string theory, the leading candidate for a unified theory of quantum gravity. This resolution, known as the fuzzball conjecture, proposes that black holes are not the simple empty objects described by general relativity, but are instead complex, extended structures made of strings and other exotic constituents. The fuzzball picture was developed primarily by Samir Mathur of Ohio State University, beginning in the early 2000s, before the firewall paradox was even formulated. Mathur and his collaborators showed that in string theory, the microstates of a black hole, the different quantum configurations that all appear identical from outside are not localized at a central singularity, but instead extend throughout the region inside the event horizon. In the fuzzball picture, there would be no event horizon in the classical sense, and no singularity at the center. Instead, the entire region that would be inside a classical black hole is proposed to be filled with a complicated structure of strings and branes, the higher dimensional objects that arise in string theory. This structure would have a definite surface at roughly the same radius as the classical event horizon, but it would be a physical surface, not a mere mathematical boundary. When matter falls onto a fuzzball, according to this model, it does not pass through an event horizon and plunge toward a singularity. Instead, it interacts with the stringy structure at the surface, depositing its energy and information. The information would not be lost behind a horizon, but would remain encoded in the quantum state of the fuzzball, where it could eventually be released as the black hole evaporates. This picture naturally avoids the firewall paradox because there is no event horizon for Hawking radiation to be entangled across. The Hawking radiation is emitted from the surface of the fuzzball, not from virtual particle pairs forming near a horizon. The information is encoded in subtle correlations between the emitted particles, just as Page's argument requires, but without any conflict with the monogamy of entanglement. The fuzzball conjecture is closely related to the firewall in some respects. Both proposals suggest that something dramatic happens at the would-be horizon of a black hole, but the nature of that something is very different. A firewall destroys anything that approaches the horizon, while a fuzzball is a complex but potentially gentle surface that absorbs infalling matter without necessarily destroying it. There are significant challenges facing the fuzzball picture. The detailed structure of fuzzballs has only been worked out for certain special cases, and it is unclear whether the results generalize to realistic black holes. Some physicists argue that the fuzzball surface would be so dense and energetic that it would effectively function as a firewall, destroying infalling observers, just as the AMPS scenario predicts. Others maintain that the interaction could be gentle enough to preserve the infalling observer's experience, at least for large black holes. The construction of fuzzball solutions is technically demanding and relies heavily on the mathematical machinery of string theory. The simplest fuzzballs correspond to highly idealized black holes with special properties, such as supersymmetry, that make the calculations tractable. For these cases, explicit solutions can be constructed, showing that the classical geometry with a horizon and singularity is replaced by a smooth, horizonless geometry that caps off before reaching where the horizon would be. These explicit constructions are impressive achievements, demonstrating that string theory contains the ingredients needed to resolve black hole singularities in a concrete way. But extending the results to more realistic black holes without supersymmetry and with large masses remains challenging. The number of microstates grows exponentially with the black hole entropy, and constructing explicit solutions for typical microstates may be beyond current techniques. Despite these limitations, the fuzzball picture has been influential in shaping how physicists think about black holes. It provides a concrete realization of the idea that black holes have microstructure, that the apparently simple geometry described by general relativity conceals a rich internal structure at the quantum level. Even if the detailed fuzzball constructions do not apply directly to astrophysical black holes, they demonstrate that the resolution of black hole paradoxes may require radical revision of our classical intuitions. The relationship between fuzzballs and firewalls has been debated extensively. Some physicists view them as competing proposals, one replacing the horizon with a gentle surface, and the other with a violent one. Others see them as potentially compatible, with fuzzballs providing the microscopic description and firewalls emerging as an effective description when the microscopic details are averaged over. Samir Mathur, the primary architect of the fuzzball program, has argued that fuzzballs avoid the firewall paradox entirely. In his view, the AMPS argument assumes that the near-horizon region is described by the vacuum state of quantum field theory, which is what generates the problematic entanglement. But for fuzzballs, the near-horizon region is not vacuum. It is filled with stringy structure that modifies the quantum state. The entanglement structure is different from what AMPS assumed, and the contradiction that led to firewalls does not arise. Critics have questioned whether this resolution truly addresses the paradox. They argue that even if fuzzballs exist, the effective description for typical microstates should resemble the classical black hole geometry, including a near-horizon region that looks approximately like vacuum to a semi-classical observer. If this is the case, the AMPS argument would still apply, and some form of firewall or dramatic effect would be needed to resolve the entanglement paradox. The debate between fuzzballs and firewalls reflects a broader tension in how physicists approach quantum gravity. The fuzzball approach is bottom-up, starting from the detailed microscopic description provided by string theory and attempting to build up to macroscopic physics. The firewall approach is top-down, starting from general principles like unitarity and effective field theory, and deducing consequences for the physics of horizons. Both approaches have their merits and limitations, and a complete understanding of black holes will likely require insights from both perspectives. The debate between fuzzballs and firewalls reflects a deeper uncertainty about the nature of black holes in string theory. Both proposals agree that the classical picture of an empty interior bounded by an event horizon is incorrect, but they disagree about what replaces it. Resolving this disagreement will require a better understanding of string theory in the strong gravity regime, a notoriously difficult problem that remains at the frontier of theoretical physics. What makes the fuzzball picture particularly appealing to some physicists is that it provides a concrete microscopic model for black hole entropy. In the early 1970s, Jacob Bekenstein proposed that black holes have entropy proportional to the area of their event horizon, a formula later confirmed by Hawking's calculation of the radiation temperature. But this entropy formula raised an immediate question. Entropy is supposed to count the number of microscopic configurations that correspond to a given macroscopic state. So what are the microstates of a black hole? In classical general relativity, black holes have no hair, meaning they are completely characterized by just three quantities: mass, electric charge, and angular momentum. There seem to be no additional degrees of freedom that could account for the enormous entropy suggested by Bekenstein's formula. The fuzzball picture resolves this puzzle by identifying the microstates with different configurations of the stringy structure inside the black hole. Each microstate corresponds to a different fuzzball geometry, and counting these geometries gives the correct entropy. This success in accounting for black hole entropy is one of the major achievements of string theory and provides strong evidence that the fuzzball picture, or something like it, is on the right track. Whether it can fully resolve the firewall paradox remains an open question, but it demonstrates that string theory has the resources to address some of the deepest problems in black hole physics. In the years following the original firewall paper, theoretical physics witnessed a series of remarkable developments that brought new hope for resolving the information paradox and the firewall puzzle. These developments centered around the page curve and the concept of entanglement islands, represent some of the most significant progress in quantum gravity in decades. The key breakthrough came in 2019 and 2020, when several groups of physicists showed that the page curve, the characteristic rise and fall of entanglement entropy that unitarity demands, can be derived from gravitational calculations. This was a crucial test that any proposed resolution to the information paradox must pass. For decades, physicists had argued that black hole evaporation should follow the page curve, but no one could actually compute it from first principles. The new calculations changed that. The work built on the ADAS-CFT correspondence, the theoretical framework that relates gravitational physics in anti-de Sitter space to a non-gravitational quantum field theory on its boundary. By carefully computing the entanglement entropy of the radiation in certain model systems, researchers showed that it indeed followed the page curve, rising initially and then falling after the page time. The calculations revealed a surprising new ingredient: entanglement islands. These are regions inside the black hole that, according to the entropy calculation, should be considered part of the radiation's entanglement wedge, the region whose quantum information is accessible to an observer collecting the Hawking radiation. Before the page time, the entanglement wedge is entirely outside the black hole, as one would naively expect. But after the page time, an island region behind the horizon becomes part of the wedge, fundamentally changing the structure of quantum correlations. The appearance of islands is deeply counterintuitive. It suggests that information that appears to be trapped inside the black hole is actually accessible to the outside observer, at least in some quantum sense. This does not mean the observer can literally send a probe into the black hole and retrieve the information. Rather, it means that the quantum state of the radiation contains all the information needed to reconstruct what is inside the island, even though the island is causally disconnected from the radiation. Jeffrey Pennington, at the time a graduate student at Stanford University, and Ahmed Almheri, one of the original AMPS authors, were among the key contributors to this breakthrough. Working in parallel with Netta Engelhardt of MIT and others, they developed a formula for computing the entropy of Hawking radiation that naturally incorporates the island contribution. The formula, an extension of the Ryuta-Kayanagi formula that relates entanglement entropy to geometric quantities, provided a precise mathematical framework for understanding how information escapes from black holes. The island formula has a beautiful structure. It instructs you to compute the entropy by finding certain special surfaces called quantum extremal surfaces, then minimizing over all possible such surfaces. Before the page time, the minimum is achieved by a trivial surface that does not include any island. After the page time, a new extremal surface appears that does include an island, and this new surface gives a smaller entropy. The transition between these two configurations is what produces the turnover in the page curve. This progress was celebrated as a major step toward resolving the information paradox. If the page curve can be derived from gravitational calculations, then unitarity is preserved, and information is not lost. The black hole can evaporate completely, returning all the information it swallowed in the form of subtle correlations in the Hawking radiation. The technical details of the island calculations are fascinating and reveal deep connections between gravity and quantum information. The central tool is the quantum extremal surface formula, a generalization of the Ryuta-Kayanagi formula that computes holographic entanglement entropy. The original Ryuta-Kayanagi formula, proposed in 2006, states that the entanglement entropy of a region in a boundary theory is proportional to the area of the minimal surface in the bulk that bounds that region. This formula beautifully connects quantum information, as measured by entanglement entropy, to geometric quantities, as measured by surface areas. The quantum extremal surface formula extends this by including not just the area of the surface, but also the entropy of quantum fields in the region enclosed by the surface. This quantum correction becomes important when the matter entropy is comparable to the geometric contribution, which happens during black hole evaporation. The formula instructs us to find surfaces that extremize the sum of the geometric area term and the matter entropy term, then to take the minimum over all such extremal surfaces. For an evaporating black hole, there are two competing extremal surfaces. One is the empty surface that does not include any island, giving an entropy contribution from the matter fields alone. Early in the evaporation, this surface dominates, and the entropy of the radiation grows steadily as more Hawking particles are emitted. The other surface includes an island region inside the black hole, and its entropy contribution includes a geometric term from the island boundary plus a matter term from the fields outside the island. The remarkable discovery was that after the page time, the island surface gives a smaller entropy than the no-island surface. The geometric term from the island boundary, which is proportional to the black hole's horizon area and hence to its Bekenstein-Hawking entropy, decreases as the black hole shrinks. Eventually, this decreasing contribution beats the increasing contribution from the matter-only calculation, and the island's surface becomes dominant. This is the transition that produces the turnover in the page curve. The physical interpretation of islands is subtle and still being developed. The island is a region inside the black hole that appears to be encoded in the radiation outside. The quantum state of the radiation contains enough information to reconstruct what is happening in the island, even though the island is behind the horizon and causally disconnected from the radiation. This could imply that the fundamental description of quantum gravity is intrinsically non-local in ways that our semi-classical picture does not capture. Some physicists interpret islands as evidence that the black hole interior is not truly separate from the exterior, but is instead encoded in it holographically. The island is not a region that an external observer can probe directly, but it is a region whose information is accessible in principle through the radiation. This interpretation connects to the holographic principle and the idea that spacetime is emergent from quantum information. Others are more cautious, noting that the island calculations are performed in specific models that may not capture all the features of realistic black holes. The models typically involve two-dimensional gravity or black holes in anti-de Sitter space, which have special properties that may not generalize. Extending the island formalism to four-dimensional black holes in flat space-time remains an active area of research. The connection between islands and firewalls is also complex. The island calculations suggest that information can be recovered from the radiation, which seems to support the unitarity of black hole evaporation, but they do not directly address the experience of an infalling observer or the entanglement structure near the horizon. It is possible that islands provide the mechanism for information recovery while firewalls still exist to enforce the monogamy of entanglement. Alternatively, the existence of islands might somehow modify the entanglement structure in a way that avoids the need for firewalls. The theoretical community remains divided on these questions. Some argue that the island calculations have essentially resolved the information paradox, showing that information is preserved through a specific mechanism that involves quantum gravity effects at the horizon. Others maintain that important puzzles remain, particularly regarding the experience of infalling observers and the fine-grained structure of the horizon region. What is clear is that the island calculations have provided powerful new tools for studying black hole evaporation and have revealed connections between seemingly disparate areas of physics. The interplay between gravity, quantum mechanics, and information theory continues to generate insights that would have seemed impossible just a few years ago. But what does this progress say about firewalls? Here, the situation is more nuanced. The island calculations are performed in a semi-classical approximation, assuming that the geometry of spacetime can be treated classically while quantum effects are incorporated through matter fields. This approximation does not resolve the fine-grained structure of the horizon, so it cannot directly tell us whether a firewall exists. Some physicists argue that the success of the island calculations suggests there is no firewall. If information can escape from the black hole through the island mechanism, then perhaps the entanglement structure near the horizon is not as problematic as the AMPS argument suggested. The firewall might be an artifact of asking the wrong questions or making inappropriate assumptions rather than a genuine feature of black hole physics. Others are more cautious, pointing out that the island calculations do not resolve all the conceptual puzzles raised by AMPS. The monogamy of entanglement still seems to create problems near the horizon, and it is unclear how the island picture interfaces with the experience of an infalling observer. The firewall debate, while perhaps less heated than it was in the years immediately following the original paper, remains unresolved. What seems clear is that the traditional picture of black holes with a smooth event horizon surrounding an empty interior cannot be the complete story. Whether the correct description involves firewalls, fuzzballs, islands, wormholes, or something else entirely, black holes are stranger and more quantum than the classical picture suggests. The progress of the past decade has not eliminated the puzzles, but has revealed new structures and tools for addressing them. The current consensus, if there is one, is that information is preserved in black hole evaporation, consistent with the unitarity of quantum mechanics. But the mechanism by which this happens, and the implications for the experience of observers near black holes, remain subjects of active research and debate. The firewall paradox has not been definitively resolved. Rather, it has been incorporated into a broader framework of puzzles and partial solutions that are gradually revealing the quantum nature of spacetime. The firewall hypothesis and the debates it has sparked are not merely abstract philosophical puzzles. They strike at the heart of some of the deepest questions humans have ever asked about the nature of reality. What is space? What is time? How do they relate to matter and energy? And what happens at the boundaries of the possible, in the extreme environments where our best theories break down? General relativity and quantum mechanics are the two pillars of modern physics, and they are spectacularly successful in their respective domains. General relativity describes gravity as the curvature of spacetime, explaining everything from the orbit of Mercury to the expansion of the universe. Quantum mechanics describes the behavior of matter and energy at the smallest scales, explaining everything from the periodic table to the operations of lasers and transistors. But these two theories do not fit together. Their mathematical structures are fundamentally different, and their physical pictures of reality are deeply incompatible. General relativity treats spacetime as a smooth, continuous fabric that can be stretched and curved by the presence of matter and energy. Quantum mechanics treats the physical world as fundamentally discrete and probabilistic, with observables that do not have definite values until they are measured. For most practical purposes, this incompatibility does not matter. Gravity is negligibly weak at the scales where quantum effects are important, and quantum effects are negligibly small at the scales where gravity is important. We can use general relativity to describe the motion of planets and galaxies, quantum mechanics to describe atoms and molecules, and never worry about reconciling the two. But there are situations where both theories should be relevant, where gravity is strong and quantum effects are significant. The interior of black holes is one such situation. The early universe, in the moments immediately following the Big Bang, is another. In these extreme environments, our two best theories contradict each other, and we have no fully satisfactory replacement. The firewall paradox is a manifestation of this deeper problem. It arises because we are trying to apply quantum mechanics to systems that are also governed by strong gravity, and the two descriptions do not agree. The paradox does not tell us which description is correct. Rather, it tells us that something new is needed, a theory of quantum gravity that can encompass both regimes. String theory is the leading candidate for such a theory, and much of the work on firewalls, fuzzballs, and islands has been conducted within its framework. But string theory remains incomplete, with many aspects not fully understood. It provides a rich toolbox for exploring quantum gravity, but is not yet delivered the clear, unified picture that physicists seek. Other approaches to quantum gravity exist, including loop quantum gravity and various discrete models of spacetime. These approaches make different predictions about black holes and may resolve the information paradox in different ways, but none has yet achieved the level of mathematical rigor and physical predictiveness that would be needed to definitively settle the debates. The firewall paradox has also had philosophical implications, challenging our intuitions about the nature of reality. The idea that space might end at the horizon of a black hole, that the interior we thought existed is actually a wall of fire or something stranger still, forces us to question what we mean by existence and reality. If different observers disagree about whether there is a region of space behind the horizon, who is right? Is there a fact of the matter, or is reality itself observer-dependent in ways we have not previously imagined? These questions connect the firewall debate to long-standing puzzles in the foundations of quantum mechanics, particularly the measurement problem and the interpretation of the quantum state. They also connect to philosophical questions about the nature of space and time, the meaning of physical laws, and the limits of human knowledge. The firewall is not just a physics problem, it is a probe into the deepest mysteries of existence. Some physicists find this situation exhilarating, a sign that we are on the verge of profound discoveries that will transform our understanding of the universe. Others find it frustrating, a reminder of how far we still have to go before we can claim to truly understand the cosmos. But all agree that the questions raised by black holes and the firewall paradox are among the most important in all of science. As we contemplate these profound mysteries, let us return to that image of floating in space, observing the warped light around a distant black hole. What seems like a simple astronomical object is actually a window into the deepest questions physics can ask. The Firewall Hypothesis, whether ultimately correct or not, has illuminated the path forward, revealing the gaps in our understanding that must be filled before we can claim to truly comprehend the nature of reality. The event horizon of a black hole may or may not be a literal wall of fire, but it is certainly a metaphorical one, a boundary between what we know and what we do not, between the physics we have mastered and the physics that still eludes us. Crossing that boundary, intellectually if not physically, is the great challenge facing theoretical physics in the 21st century. The resolution to the firewall paradox, when it comes, will likely require new ideas that we cannot yet imagine. Based on the current trajectory of research, it may reveal that spacetime is emergent, woven from more fundamental quantum constituents. It could show that information has properties we have not yet discovered, flowing and transforming in ways that preserve unitarity while also respecting the geometry of gravity. Some physicists even speculate it may challenge the basic framework of quantum mechanics itself, forcing us to revise principles we have trusted for nearly a century. These possibilities remain open, awaiting the theoretical breakthroughs that will finally resolve this profound puzzle. Whatever the resolution, the journey to find it has already yielded profound insights. The connections between entanglement and geometry, the role of computational complexity in black hole physics, the emergence of islands and wormholes from gravitational calculations. These are lasting contributions that will shape physics for generations to come. And so we leave our contemplation of the firewall with more questions than answers, but perhaps that is as it should be. The universe is vast and strange, filled with wonders that exceed our imagination and puzzles that exceed our understanding. Black holes, those ultimate expressions of gravitational collapse, sit at the intersection of our deepest theories, demanding that we push beyond what we know into territory where no one has gone before. If these explorations of the cosmos have provided you with moments of wonder and peaceful contemplation, please consider subscribing to the channel. Each journey we take together, whether into the depths of black holes or the breadths of the observable universe, is an opportunity to connect with the profound mysteries that surround us, to find peace in the vastness and beauty of existence, and to marvel at the capacity of the human mind to reach toward the infinite. Until next time, rest well in the knowledge that the universe, for all its mysteries, continues to reveal itself to those who look with curiosity and wonder. The firewall may blaze at the edge of possibility, but the light of understanding grows ever brighter, illuminating paths we have only begun to explore. The cosmos awaits, patient and eternal, ready to share its secrets with those willing to seek them. Good night. Now let us delve even deeper into the mathematical and physical foundations that underpin this remarkable paradox. For in understanding the details, we find both the beauty of the argument and the profound challenges it poses to our understanding of nature. The mathematics of quantum entanglement lies at the very heart of the firewall paradox. And to truly appreciate the argument, we must understand what entanglement means in a precise quantitative sense. When we speak of two quantum systems being entangled, we are describing a situation where the quantum state of the combined system cannot be written as a simple product of the states of the individual parts. The systems are correlated in a way that transcends any classical description, bound together across space by invisible threads of quantum probability. Consider the simplest possible example: 2 qubits, the quantum analogs of classical bits. A classical bit can be either 0 or 1, and 2 classical bits can be in one of 4 states: 0, 0, 0, 1, 1, 0, or 1, 1. A quantum bit, by contrast, can exist in a superposition of 0 and 1 simultaneously, its state described by a vector in a two-dimensional complex vector space. When we have 2 qubits, the combined system lives in a 4-dimensional space, corresponding to the 4 basis states we listed for classical bits. If the 2 qubits are completely independent, The state of the combined system can be written as a tensor product of the individual states. We might have, for example, the first qubit in an equal superposition of 0 and 1, and the second qubit likewise in an equal superposition. The combined state would then be a product, exhibiting no correlation between the qubits. Measuring the first qubit tells us nothing about the second, but quantum mechanics also allows states that cannot be written as such products. The most famous example is the Bell state, where the two qubits are in an equal superposition of both being 0 and both being 1. This state cannot be decomposed into a product of individual qubit states. The qubits are fundamentally linked. If we measure the first qubit and find 0, the second qubit instantly becomes 0 as well, regardless of the distance separating them. If we find 1, the second becomes 1. The correlation is perfect and instantaneous, though it cannot be used to send information faster than light. The degree of entanglement can be quantified using a measure called the entanglement entropy. For a pure state of two systems, we can compute the entropy of either subsystem by tracing over the degrees of freedom of the other. This entropy measures the amount of uncertainty or mixedness introduced by ignoring one part of the entangled system. For a product state, the entanglement entropy is 0, reflecting the fact that the subsystems are independent. For a maximally entangled state, like the Bell state, the entropy is maximal, 1 bit for 2 qubits. The monogamy of entanglement constrains how this entropy can be distributed across multiple parties. If qubits A and B are maximally entangled, each having 1 bit of entanglement entropy with respect to the other, then neither A nor B can have any entanglement with a third qubit C. The total entanglement capacity of a qubit is limited, and maximal entanglement with one partner exhausts this capacity entirely. This mathematical constraint has profound implications for the firewall paradox. The outgoing Hawking particle must have maximal entanglement with its infalling partner to ensure that the quantum state near the horizon is the vacuum state, free from high-energy excitations. But after the page time, the same particle must also have significant entanglement with the previously emitted radiation to allow information to be recovered from the black hole. Monogamy says these two requirements cannot both be satisfied, leading inexorably to the conclusion that something must give. The page time itself deserves more careful examination. It is not simply a random moment in the black hole's evolution, but rather a precisely defined transition point determined by the fundamental physics of quantum information. Don Page's original analysis showed that if a quantum system consisting of many subsystems evolves unitarily, the entanglement entropy of any subsystem initially increases as correlations spread throughout the system, but eventually begins to decrease as the subsystem becomes increasingly correlated with the information already released. For a black hole, Page estimated that this transition occurs when the black hole has radiated away approximately half of its initial entropy, which corresponds to losing a significant fraction of its original mass. The exact numbers depend on details of the evaporation process, but Page's calculations for a black hole that emits primarily photons and gravitons found that the maximum entanglement entropy is reached after about 54% of the evaporation time, when the black hole has lost about 40% of its original Bekenstein-Hawking entropy. These numbers may seem like arcane details, but they have crucial implications for the firewall paradox. The firewall, if it exists, would not appear immediately when the black hole forms, but only after the page time, when the entanglement structure of the Hawking radiation becomes incompatible with a smooth horizon. This means that young black holes, those that have not yet radiated away half their entropy, would still present peaceful horizons to infalling observers, at least according to the firewall argument. For astrophysical black holes, the time to reach the page time is inconceivably long. A black hole with the mass of the Sun would have a Hawking temperature of only about 60 nanokelvins, far colder than the cosmic microwave background that bathes the universe. Such a black hole would actually absorb more radiation from the CMB than it emits, gaining mass rather than losing it. Only if the universe continues to expand and cool for many orders of magnitude longer than its current age would such a black hole begin to evaporate. And even then, the page time would lie far in the future. The timescales involved are truly astronomical. For a solar mass black hole evaporating in isolation, the total evaporation time would be approximately 10 to the 67th years, a number so vast that it defies comprehension. The page time, roughly half of this, would still be tens of orders of magnitude longer than the current age of the universe. No black hole that currently exists could possibly have reached its page time, let alone developed a firewall. This observation has led some physicists to question the practical relevance of the firewall paradox. If firewalls can only exist for black holes far smaller than any that nature could produce through stellar collapse, and only after timescales vastly exceeding the lifetime of the cosmos, what difference does it make? The answer is that the firewall paradox is not primarily about astrophysical black holes, but about the fundamental structure of physical law. The paradox reveals an inconsistency in our theoretical framework that must exist regardless of whether we can ever observe its consequences directly. In science, consistency is paramount. A theory that makes contradictory predictions, even in regimes we cannot access experimentally, is fundamentally flawed. The firewall paradox shows that our current understanding of black holes, based on a combination of general relativity, quantum field theory, and the principles of quantum information, contains such a contradiction. Resolving this contradiction, even if the resolution has no practical implications, is essential for developing a complete and coherent theory of nature. Let us now examine the thermodynamics of black holes in greater detail, for this subject provides essential context for understanding both Hawking radiation and the information paradox it creates. The connection between black holes and thermodynamics was one of the most surprising discoveries of 20th century physics, revealing a deep unity between gravity, quantum mechanics, and statistical physics. The story begins with the observation that black holes obey certain laws that are formally analogous to the laws of thermodynamics. The area of a black hole's event horizon never decreases, just as the entropy of an isolated system never decreases according to the second law. In fact, when two black holes merge, the area of the resulting black hole is always greater than the sum of the original areas, a direct analog of the entropy increase in irreversible thermodynamic processes. Jacob Bekenstein, in the early 1970s, took this analogy seriously and proposed that black holes actually possess entropy, with the entropy being proportional to the area of the event horizon measured in Planck units. This was a radical idea because in classical general relativity, black holes are completely characterized by just three quantities: mass, charge, and angular momentum, and seem to have no internal structure that could account for entropy. Bekenstein argued that the entropy was nonetheless real, reflecting a fundamental limitation on the information that can be extracted from a black hole. Stephen Hawking initially opposed Bekenstein's idea, arguing that if black holes had entropy, they would also have to have temperature, and a hot object should radiate. But black holes, by definition, do not radiate. Nothing can escape from beyond the event horizon. Hawking's objection seemed decisive until he himself discovered that quantum mechanics changes the picture. By applying quantum field theory to the curved spacetime near a black hole horizon, Hawking showed that black holes do radiate, emitting a thermal spectrum of particles at a temperature inversely proportional to their mass. This Hawking temperature is extremely low for astrophysical black holes, but it is non-zero, vindicating Bekenstein's thermodynamic reasoning. The Hawking temperature and the Bekenstein entropy together satisfy the standard thermodynamic relations, with the surface gravity of the black hole playing the role of temperature and the horizon area playing the role of entropy. This connection between black hole physics and thermodynamics has been enormously fruitful, leading to insights about the nature of space, time, and information. The Bekenstein-Hawking entropy formula tells us that the entropy of a black hole is proportional to its area, not its volume. This suggests that the information content of a region of space is bounded by its boundary, not its bulk, a principle that has become known as the holographic principle. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind in the 1990s, proposes that all the physics of a region of space can be encoded on its boundary, much as a two-dimensional hologram can contain all the information needed to reconstruct a three-dimensional image. This principle has been made precise in the context of the AD-S-CFT correspondence, where gravity in a higher dimensional anti-de Sitter space is exactly equivalent to a non-gravitational quantum field theory on its lower dimensional boundary. The holographic principle has profound implications for our understanding of space and time. Based on what we can infer from this principle, the three spatial dimensions we perceive may be emergent, arising from more fundamental physics that lives on a two-dimensional surface. The degrees of freedom that we interpret as living in the bulk of space could actually be boundary degrees of freedom that have been repackaged in a way that mimics three-dimensional physics. This perspective has been crucial for progress on the information paradox, providing tools for tracking how information flows during black hole evaporation. The temperature of a black hole, while conceptually important, is incredibly faint for any black hole we might encounter in nature. A black hole with the mass of the Sun has a Hawking temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates space at about 2.7 Kelvin. This means that astrophysical black holes are not truly evaporating. They are actually absorbing energy from their environment faster than they emit it through Hawking radiation. Only a black hole smaller than approximately the mass of the Moon, around 10 to the 23rd kilograms, would have a Hawking's temperature exceeding the cosmic microwave background temperature. Such a black hole would be genuinely evaporating, emitting more radiation than it absorbs. But black holes this small cannot form from stellar collapse. The smallest black holes that can form from dying stars are several solar masses. The only way to create smaller black holes would be through exotic processes in the early universe, potentially producing what are called primordial black holes. If primordial black holes were created with small enough masses in the moments after the Big Bang, they might have been evaporating ever since and could be nearing the end of their lives today. A black hole initially created with a mass of about 10 to the 12th kilograms, roughly the mass of a modest asteroid, would have a lifetime of about 14 billion years, comparable to the current age of the universe. Such a black hole would now be in its final stages of evaporation, emitting increasingly energetic radiation as its mass dwindles and its temperature rises. The final moments of black hole evaporation are particularly dramatic. As the black hole shrinks, its temperature rises, and it emits radiation at ever higher energies. In the last fraction of a second, the temperature reaches astronomical values, and the black hole explodes in a burst of high-energy gamma rays and other particles. This final explosion releases an energy equivalent to millions of nuclear bombs, all compressed into a volume smaller than an atomic nucleus. The physics of this final explosion is poorly understood because it occurs in a regime where both quantum mechanics and gravity are important simultaneously. Our current theories cannot reliably describe what happens when a black hole's mass approaches the Planck mass, about 22 micrograms. This is where a true theory of quantum gravity would be needed, and its absence represents one of the great gaps in our understanding of nature. The final state of black hole. Evaporation is directly relevant to the information paradox. If the black hole evaporates completely, leaving only radiation behind, what happens to the information that fell in? The radiation is apparently thermal, carrying no information about the black hole's history. Unitarity seems to be violated unless the information is somehow encoded in subtle correlations within the radiation that our current calculations do not capture. The firewall paradox sharpens this question by focusing on the entanglement structure of the Hawking radiation. The paradox does not depend on the details of what happens in the final explosion, but rather on the properties of the radiation emitted during the main phase of evaporation, after the page time. Even if we cannot describe the final moments, the Ampeus argument applies to the bulk of the evaporation process, where our theoretical tools should be reliable. Let us now explore the concept of the stretched horizon in greater detail, for it plays a crucial role in the framework of black hole complementarity and helps illuminate the physical picture behind the firewall paradox. The stretched horizon is not the mathematical event horizon itself, but rather a surface located about 1 Planck length outside the horizon, where quantum gravitational effects first become significant. From the perspective of an observer hovering just outside a black hole, supported against gravity by powerful rockets, the stretched horizon appears as an incredibly hot, dense membrane. This is a consequence of the extreme blue shifting that occurs near the horizon. Hawking radiation, which appears as low-temperature thermal radiation to a distant observer, is blue shifted to enormous energies near the horizon. The effective temperature at the stretched horizon can be estimated by dividing the Hawking temperature by the gravitational redshift factor, which approaches infinity at the horizon itself. The result is a temperature on the order of the Planck, Temperature, about 10 to the 32 Kelvin. This is the highest temperature that has physical meaning, the temperature at which the thermal energy of a particle equals the Planck energy, and quantum gravitational effects dominate. At the stretched horizon, the standard picture of smooth space-time breaks down, and new physics must take over. In the framework of black hole complementarity, the stretched horizon is where infalling information becomes thermalized and eventually re-emitted as Hawking radiation. An external observer sees information fall onto the stretched horizon, where it is rapidly scrambled and mixed with the other degrees of freedom of the horizon. The scrambling time, the time required for information to spread across the entire horizon, is remarkably short, only logarithmically dependent on the black hole's entropy. Patrick Hayden, John Preskill, and others showed that black holes are the fastest scramblers in nature, mixing information faster than any other known physical system. This rapid scrambling is crucial for information recovery. It ensures that information deposited on the horizon is quickly distributed across all the emitted Hawking radiation, making it recoverable in principle, even if the process of decoding it is extraordinarily complex. The notion of scrambling connects the physics of black holes to the theory of quantum computation and complexity. Decoding the Hawking radiation to recover the information that fell into a black hole would require performing a quantum computation of staggering complexity. Daniel Harlow and Patrick Hayden showed that the time required for this computation is exponential in the entropy of the black hole, vastly exceeding the evaporation time itself. This observation led to a proposed resolution of the firewall paradox based on computational complexity. The AMPS argument relies on an observer who first collects the Hawking radiation, processes it to extract information, and then jumps into the black hole to check for a firewall. But if the computation required to extract the information takes longer than the black hole's lifetime, the experiment can never be performed. The firewall exists in some sense, but no observer can ever verify it because the required measurements are computationally infeasible. This complexity-based resolution is clever but controversial. It does not eliminate the firewall so much as hide it behind a barrier of computational intractability. Many physicists find this unsatisfying, arguing that physical reality should not depend on the computational capabilities of observers. If a firewall exists, it exists regardless of whether anyone can detect it through elaborate quantum computations. The debate over computational complexity and its role in physics reflects a broader tension in the field. Traditional physics describes what is, not what can be known or computed, but quantum mechanics, with its emphasis on measurement and observation, blurs this distinction. And quantum gravity, dealing with regimes where spacetime itself may be subject to quantum uncertainty, might require an even more radical rethinking of the relationship between reality and observation. The stretched horizon also raises questions about the experience of infalling observers. According to complementarity, an observer who falls freely through the horizon experiences nothing unusual, passing smoothly into the black hole interior. But from the perspective of an external observer, the same infalling observer is absorbed by the stretched horizon, thermalized, and eventually re-emitted as Hawking radiation. These two descriptions seem contradictory, and complementarity holds that they are merely complementary views of the same underlying reality. valid in their respective domains, but not simultaneously observable. The AMPS argument challenges this comfortable picture by constructing a thought experiment, where the two views come into direct conflict. After the page time, the entanglement structure of the Hawking radiation implies that the stretched horizon cannot be both thermalized, as required for information recovery, and smooth as required for free fall through the horizon. The firewall emerges as the resolution of this conflict, a genuine physical effect that destroys the infalling observer and prevents the contradiction from being observed. Let us now consider the profound question of what the interior of a black hole is actually like. This is one of the deepest puzzles in all of physics, and the firewall debate is intimately connected to it. In classical general relativity, the interior of a black hole is a well-defined region of spacetime, containing the singularity at its center and connected to the exterior by the smooth event horizon. But in quantum gravity, this simple picture may be radically wrong. If the firewall hypothesis is correct, there may be no interior at all, at least not after the page time. This would suggest that the event horizon marks not a threshold that can be crossed but a true boundary of space-time, beyond which nothing exists. The singularity, traditionally hidden at the center of the black hole, would be replaced by the firewall at the horizon, a wall of destruction that terminates the space-time itself. This interpretation, while still debated, represents one possible reading of what the firewall paradox implies. This is a shocking possibility, and many physicists find it deeply unappealing. The interior of a black hole, whatever its properties, seems like it should exist. General relativity describes it in detail, tracing the world lines of infalling observers as they plunge toward the singularity. To say that this entire region is a fiction, an artifact of classical reasoning that breaks down when quantum effects are included, would be a profound revision of our understanding of space and time. But there are reasons to take this possibility seriously. The interior of a black hole has always been somewhat problematic, containing the singularity where physical quantities become infinite and our equations break down. If the singularity is a sign that classical general relativity is failing, perhaps the entire interior should be viewed with suspicion. The firewall might be nature's way of enforcing the breakdown of classical spacetime at the horizon rather than hiding it at the singularity. The fuzzball proposal offers a different picture, where the interior is replaced not by a firewall, but by a complex, stringy structure that extends to the horizon. In this view, the classical interior is an illusion arising from coarse graining over many microstates, none of which actually has a smooth interior. The fuzzball picture is perhaps gentler than the firewall, but it similarly implies that the classical description of the black hole interior is fundamentally wrong. There are also proposals that preserve the interior while avoiding the firewall. The ER equals EPR conjecture suggests that the interior could be connected to the exterior through wormholes, linking the entanglement between Hawking particles in a way that might resolve the monogamy conflict. In this view, the interior exists, but would be woven into a complex web of quantum connections that our naive picture does not capture. The state dependence proposals, developed by Kyriakos Papadodimas and Suvrat Raju, suggest that the operators describing the black hole interior may depend on the overall quantum state in a highly non-local way, Under this interpretation, the interior exists, but its description would require knowing the state of the entire system, including all the emitted Hawking radiation. This could resolve the firewall paradox by making the interior effectively inaccessible to any observer who does not have complete knowledge of the quantum state. Each of these proposals has its own challenges and critics. The fuzzball picture struggles to explain how smooth geometry emerges for typical microstates. The ER equals EPR conjecture has not been fully formalized and may conflict with other principles of physics. State dependence seems to violate the linearity of quantum mechanics and raises puzzles about what it means for an observer to interact with the interior. The lack of consensus reflects the fundamental difficulty of the problem. Black hole interiors lie at the intersection of quantum mechanics and gravity. In a regime where our best theories do not agree and our experimental tools cannot reach, progress will likely require new theoretical insights, perhaps from string theory, loop quantum gravity, or approaches not yet imagined. What seems clear is that the traditional picture of the black hole interior, a smooth space-time region containing a singularity, cannot be the whole truth. Quantum effects modify the interior in ways that we are only beginning to understand, whether through firewalls, fuzzballs, wormholes, or something else entirely. The resolution of the firewall paradox will likely reshape our understanding of what it means for a region of space-time to exist. The philosophical implications of the firewall debate extend beyond the specific question of black hole interiors to touch on fundamental issues about the nature of physical reality. The debate raises questions about the relationship between observation and existence, the role of information in physics, and the limits of human knowledge about the universe. Consider the question of whether the interior of a black hole exists. In classical physics, existence is a straightforward concept. A region of space-time exists if the laws of physics describe events occurring there. But in quantum mechanics, the situation is more subtle. The state of a quantum system is described by a wave function that may not correspond to any definite classical configuration. And in quantum gravity, the geometry of space-time itself may be subject to quantum uncertainty, making the very question of whether a region exists potentially meaningless. The firewall debate highlights this conceptual difficulty. Different observers, applying the principles of quantum mechanics and general relativity in their respective domains, arrive at conflicting conclusions about what exists near the horizon of a black hole. Complementarity attempted to resolve this by declaring both descriptions valid, but not simultaneously observable. The firewall paradox challenged this resolution, suggesting that a more radical revision is needed. Some physicists have proposed that the interior of a black hole is not a fact about the universe, but a fact about certain observers' descriptions of the universe. In this view, the interior exists for Alice, who falls through the horizon, but does not exist for Bob, who remains outside. There is no absolute fact about the interior. It depends on the observer. This is a form of relativism about physical reality that goes beyond the relativism of special relativity, where different observers disagree about simultaneity and length, but agree on the underlying events. Such observer dependence is controversial, and many physicists resist it. Science traditionally aims to describe the world as it is, independent of who is observing it. If the existence of space-time regions depends on the observer, what remains of the notion of an objective physical reality? These are not merely academic questions. They affect how we interpret quantum mechanics and pursue a theory of quantum gravity. The role of information in physics has also been transformed by the firewall debate. In classical physics, information is a useful concept, but not a fundamental one. The laws of physics describe the evolution of physical quantities, like position, momentum, and energy. Information is a derived concept that tracks correlations between these quantities. But in quantum mechanics, information plays a more central role. The wave function contains complete information about a quantum system, and unitarity ensures that this information is preserved under time evolution. The black hole information paradox elevates information to a fundamental principle that must be respected even in the most extreme gravitational environments. The firewall paradox goes further, showing that the preservation of information can have dramatic physical consequences, potentially destroying the smooth geometry that general relativity predicts near black hole horizons. Information is not merely a bookkeeping device, but a constraint on the structure of physical law. This perspective has led to what some physicists call the it from qubit program, the idea that spacetime geometry emerges from quantum information. According to this hypothesis, the fundamental building blocks of the universe are not particles or fields, but qubits, units of quantum information, and the geometry of space and time arises from the way these qubits are entangled. The ER equals EPR conjecture can be seen as an expression of this idea, proposing that geometric connections in spacetime are manifestations of quantum entanglement. While these ideas remain theoretical proposals rather than established facts, they represent an active frontier of research. If this program succeeds, it would represent a revolution in physics comparable to the quantum revolution of the early 20th century. Space-time, long considered the stage on which physics plays out, would be revealed as a derived concept, an approximation that emerges from more fundamental quantum dynamics. In this scenario, the firewall paradox, rather than being a problem to be solved, would be a signpost pointing toward this deeper understanding. This remains one of several possible directions that future research might take. As we approach the end of our exploration, let us reflect on what the firewall hypothesis teaches us about the scientific enterprise itself. The paradox emerged not from observation, but from pure thought, from carefully reasoning about the implications of principles we believe to be true. It forced physicists to confront uncomfortable conclusions and to question assumptions they had long taken for granted. This is how fundamental physics often progresses. Without the ability to directly probe black hole horizons, we must rely on theoretical consistency to guide us. The firewall paradox shows that our theories, however successful in their respective domains, cannot all be true in all circumstances. Something must change, and determining what that something is will require creativity, rigor, and perhaps ideas that have not yet been conceived. The debate has also illustrated the collaborative nature of modern physics. The original AMPS paper sparked hundreds of responses, proposals, counter-arguments, and refinements. Workshops and conferences brought together specialists from different areas: general relativity, string theory, quantum information, and condensed matter physics, each contributing insights from their particular expertise. The resolution, when it comes, will likely draw on ideas from all these fields and more. And yet, despite the intense effort of the past decade, the paradox remains unresolved. This is not a failure, but a sign of the problem's depth. The easy solutions have been tried and found wanting. What remains requires deeper understanding than we currently possess. The firewall paradox has become a testing ground for ideas about quantum gravity, a benchmark that any proposed theory must address. The journey we have taken tonight, from the classical picture of black holes to the quantum puzzles of Hawking radiation and beyond, illustrates the layered nature of scientific understanding. Each generation builds on the work of its predecessors, extending the reach of physics into new regimes and uncovering new puzzles that demand further exploration. The firewall paradox is part of this ongoing story, a chapter that is still being written. As you drift towards sleep, contemplating these cosmic mysteries, remember that the universe is vaster and stranger than any of us can fully comprehend. Black holes, those ultimate expressions of gravitational collapse, encode secrets about the nature of space, time, and reality that we are only beginning to uncover. The firewall hypothesis, whether ultimately correct or not, has illuminated the path forward, revealing the questions we must answer to achieve a complete understanding of nature. The horizon of knowledge, like the event horizon of a black hole, marks a boundary between what we know and what we have yet to discover. Crossing that boundary requires courage, persistence, and the willingness to question our most cherished beliefs. The physicists who have grappled with the firewall paradox exemplify these qualities, pushing against the limits of understanding in pursuit of deeper truth. And so we conclude our journey with a sense of wonder and anticipation. The mysteries we have explored tonight are not merely intellectual puzzles, but windows into the deepest structure of reality. The universe has revealed some of its secrets, but many more remain hidden, waiting to be discovered by those who ask the right questions and follow the evidence wherever it leads. If these explorations have brought you peace and wonder, please subscribe to the channel and share these journeys with others who might appreciate them. Each listener who joins us adds to the community of curious minds seeking to understand our place in the cosmos. Until next time, rest well in the knowledge that the quest for understanding continues, that brilliant minds around the world are working to unravel the mysteries we have discussed, and that the universe, for all its puzzles, operates according to laws that human beings can, with effort and insight, hope to comprehend. The firewall may blaze at the edge of possibility, but the light of human curiosity burns brighter still. Sleep well, and may your dreams carry you to horizons beyond imagining. Good night, and thank you for joining me on this journey through one of the most profound puzzles in all of physics.